Hello, please take a moment and check your answers from the warm-up. For number 1, you are using the special pattern of a perfect square trinomial, which factors to 2x plus 1 squared. For number 2, that's a difference of 2 squareds, so 3 plus 13x and 3 minus 13x. Keep them in that order, otherwise you'll have to factor out a negative. Number 3, 3 times 2x minus 1 times the quantity 2x minus 3. Number 4, once you factor out the 2, you have a difference of 2 squareds, so 3x plus 1 and 3x minus 1. And then for number 5, if you get everything to one side, and then you can factor out a 2, then you're going to be left with a perfect square trinomial. So you would have 3x plus 4 squared, which solves to x equals negative 4 over 3. Take a moment. You can press pause and confirm with the partner in case you missed any of that. 4.6. Solve quadratic equations by square roots. So properties of square roots. The first one is the square root of a times b is equal to the square root of a times the square root of b. This is our product property. So if I wanted to break down the square root of 36 into two different perfect squares, I can have the square root of 9 times the square root of 4. Square root of 9 is 3 times the square root of 4 is 2, which is 6. This is when they're both perfect squares, so it doesn't really look like you would ever need this, but I'm going to show you that in a moment. One thing that I'm talking about that I think we should probably list really quickly are perfect squares. Perfect squares are numbers that you can take the square root of evenly, like the first one, what's 1 squared? 1. What's 2 squared? 4. 3 squared is 9. 4 squared is 16. Then 25, 36, because you can take the square root of all these numbers evenly. 49, 64, 81, 100, 121, ... These are perfect squares. Start committing things to memory because they're going to help us out like a lot. And then the quotient one is if you divide, instead you can divide them and have two separate radicals. So if I have the square root of 4 over 9, I can look at this as the square root of 4 over the square root of 9, which simplifies to 2/3. Those perfect squares, we're going to need them for this first example. So I'm looking at the number 500, and I want to rewrite this as the product of two perfect squares. So you're going to look at your list that you had generated. What's the biggest number that goes into 500? So 121 is the biggest number that I had on there. Doesn't go in there. 100 looks pretty good to me. 100 goes into 500 evenly 5 times. So then I could write this as the square root of 100 times the square root of 5. The square root of 100 is 10, and then I still have the square root of 5. This is what it means to simplify a radical. You're basically looking for any big perfect squares, and then your final answer should have no perfect squares left over in the radical. 0 left over in the radical. Okay, so for number 2, another part of this rule is you can only multiply what's outside with what's outside, so that's going to give me 15. And then what's inside with what's inside. So the square root of 24 times the square root of 20 is going to equal the square root of 480. And then you're going to go back to your list and you're going to look for some big perfect squares that could go into 480. So going down that list, I'm not seeing anything except the number 16. So if I divide 480 by 16, I get 30. You're kind of just trusting my math on this one. I know it's a scary thought, but I want you to do that. So that's the biggest one though, truthfully. If you went down this list and tried all of these numbers, that's the biggest one. One other good hint though is there's not ever going to be one that's bigger than half of 480. So not one bigger than 240. So if you look at perfect squares starting there, like at 256 and on the way down, there's not one, I promise. So simplifying this, this is like the square root of 15 times the square root of 16 times the square root of 30. And I know that I'm right because there's also no perfect squares that go into 30. So this is the square, this is 15 times, now the square root of 16 is 4 times the square root of 30. Now I'm going to combine these two, and then 15 times 4 is 60, and then I still have the square root of 30 right there on the outside, in the inside. And that's your final answer. Part 3 square root of 25 over the square root of 81. Well, I'm going to, like I just now told you, spoiler alert, write them as two separate radicals. And then square root of 25 is 5. Square root of 81 is 9. Fun stuff. Same concept here, except we get a little bit of a hiccup. Square root of 36 is fine for me, but there aren't any perfect squares that go into 5. The only issue that we have right now is that you cannot leave it with a radical in the denominator. It's not allowed. You have to do what's known as rationalize the denominator. So you ask yourself, okay, well, what can I multiply by in order to make this radical cancel out? Well, wouldn't it be great if, when I multiply this times something, I got a perfect square here? Well, a perfect square that involves 5 would be the square root of 25. That would be great. That's my ideal situation. I don't have that yet. What do I have to multiply the square root of 5 by in order to get 25? 5. Only rule, though, is whatever you do to the denominator, you must also do to the numerator. So my new numerator is 6 radical 5, and then square root of 5 times square root of 5 is square root of 25. And the reason why I wanted to do that is because this being a perfect square, the square root of 25 is now just 5. That is what it means to rationalize your denominator. Congratulations. And next, speaking of, sometimes it's not going to be that direct, where all I have to do is multiply top and bottom by one thing. Sometimes I'm going to have to switch that up a little bit. So let's take a moment and remember about foiling to multiply. Remember first, outer, inner, last. Well, what would we get if we multiplied these? First, the 2 times 2 would be 4. Outer, the 2 times radical 3 is 2 radical 3. Inner, negative 2 radical 3. Last, minus square root 9. If that was too fast, go ahead and press pause and then just FOIL this on your own so that you're not relying on me. So 2 radical 3 minus 2 radical 3, that's nothing. Minus the square root of 9. Well, 4 minus the square root of 9 is a perfect square. That's 3 is equal to 1. Notice here, we started off with radicals all over the place, and our answer doesn't have any. It's because these are what's known as conjugates. So it's the same thing. See how these are essentially the same with one exception. The exception being one is plus and one is minus. These are conjugates because their product is always a rational number without any radicals. Just like here and just like you saw here. These would be conjugates of each other because when I multiply them, I have no radical left. When I multiplied these, no radical is left. So if I have a square root of b in my denominator like we had over here, I'm going to multiply it by radical b. If I have a plus radical b, I'm going to multiply it by a minus radical b. If they give me a minus radical b, I'm going to multiply it by a plus radical b. How will this look different? I guess if you had the radical first, then I would do square root of a minus b. Continuing on. Same thing will happen there. Okay, and then, so if it bothers you, minus b, then you could do this as well. These are conjugates. So when I multiply them, if I get any of these on the in the denominators, I can multiply by any combination of these. So given that, once you flip that over, I have radical 3 plus 7. So to rationalize it, I'm going to multiply by its conjugate. Pay very close attention because I'm going to have you do the next one on your own. So I'm going to distribute here and here, and I have 6, just kidding, I have 2 radical 3, and then 2 times 7 plus 14. I'd messed up because I can only multiply what's inside with what's inside and what's outside with what's outside. Over, now multiplying this, you can multiply that completely out. First terms, I get radical 9. Outer, I get minus 7 radical 3. Inner, plus 7 radical 3. last, minus 49, 7 times 7. So up top I have 2 radical 3 plus 14 over, these are now gone, square root of 9 is 3 minus 49, so I have 2 square root 3 plus 14 over negative 46. One more step, beautiful people. I am looking at this 2, this 14, and this 46, everything outside of the radical. And I am noticing that they all have something in common. They all can be divided by 2. Divide by 2 and divide by 2. So I get radical 3, because these cancel out, plus 7 over negative 23. There you go. Do me a favor, if you would please, go ahead and press pause and try number 7. When you're done pressing pause, I'm going to show my work for you to check yours with. Okay, nothing to reduce at the end for this one, so I have this as my answer. Go ahead and press pause and check your work with mine. Alright, so solve. We're going to solve this just as if this was just a regular old x. So first thing I'm going to do is subtract 3. And I have negative 5x squared is equal to negative 12. Then I'll divide by negative 5. And I have x squared is equal to 12 over 5. Next step for us is to get rid of this squared. The opposite of squaring, or the inverse, is to square root. So the squared and the square root cancel out, and I have x is equal to, well, it could be positive 12, square root 12 over 5, but it also could be negative. Similar to, if I told you that x squared equals 25, well, what can x be? X could be positive 5, but it could also be negative 5 too, because negative 5 squared also gives you 25. So this is the plus or minus right here, which would be fine and dandy, except that you have a radical in the denominator. So I just wrote them as separate radicals, and I'm going to go ahead and rationalize by multiplying the square root of 5 on both. So the positive and negative square root of 60 over the square root of 25, which is just 5. I started with the biggest problem and the most difficult one. So the only thing left here, though, now that I'm kind of being a little bit nitpicky, is this has a perfect square. It's 4 times 15 in my head. And then this will just stay the 5. Square root of 4 is 2. The square root of 15 stays in there, all over 5. So you have 2 radical 15 over 5, and then you just have to remember to put the plus or minus sign there at the end. Number 9, they get nice and friendly, I promise. So before I can get rid of this squared, I want to get rid of this 3. Can't distribute it because this is the quantity being squared, so I'm going to get rid of it by dividing by 3. And I have x minus 2, the quantity squared, equals 7. And then I'll square root, and then I'll square root. And I have x minus 2. As soon as you square root, that's when you put your plus or minus. Even though this is not a perfect square, you're going to put your plus or minus there. Then plus 2. And I have x is equal to, I cannot combine these because this has a radical and this does not. So this was a positive 2, so I'm going to just write 2 plus or minus radical 7. And that's it for that one. I don't need a decimal. This is an exact answer, and it's very, very accurate just the way that it is. Okay, last one. Isolate the x squared first. So I'm going to subtract 8 and subtract 8. I have x squared over 20 is equal to 7. And then I'm going to multiply both sides by 20. And I have x squared is equal to 140. And then from there, I'm going to radical and radical. And I have x is equal to positive and negative radical 140. 140, though, is 4 times 35. That 4 is my perfect square. So x is equal to positive negative 2 radical 35 for that one. Important thing to remember is just to put your plus or minus there as soon as you take the square root of a number. All right, thank you very much. That's your lesson for today, and I hope that you have a great one.